All right, guys. So I'm going to start this again one last time. If you entered in late, the link is in the chat, or you can use the website, the screen on the site. This is going to be your daily grade by participating. You won't have to do anything after this on your own if you are here in the Zoom today. So we're going to start this out as a start this way. There's some days that will be just talk for a little bit, and then I'm going to give you guys an assignment. Today will be, discussing and doing this kind of together. So then I want to ask you, get you guys the feedback on how it went at the very end. Okay, so we're good here till 2 o'clock. Um, for again, I keep posting this in the chat multiple times for the people that come in late and for people coming in late. All right, so here's what we got. This I told you guys this first unit is kind of brand new to everybody. It's called graph theory. And what is graph theory? Well, there's a definition for graph theory right there. It is probably not anything that you guys have ever seen before, but it's used in a lot of different ways in a lot of different careers and aspects online. Or I'm sorry, in different careers. And so we're going to be drawing things called graphs. And when I talk about graphs for the next 6 weeks, we're not talking about this type of graph. This is a graph you guys did in algebra 2. We're not doing that in this class. Will do a little bit of some different types of graphical displays next semester with statistics, but we're not plotting any points anymore. That's not the graph that we're talking about. So get that out of your mind for the next 6 weeks. That a graph, when I talk about a graph, this is what a graph is going to look like. This right here is what we call a graph in graph theory. It's made up of a bunch of dots and lines. The dots are called vertices or vertex if it's singular, and the lines are called edges, edges plural. So these this is what a graph is from now on, and the reason why this particular field of math is pretty important is because there's a lot of different things that you can use in graph theory, creating graphs like networks and such as this friendship network on Facebook, or any social network really. And so this is the idea that I want to get in your head is what these kind of graphs look like. And so here's another graph. This is really pretty basic. So I just want to get this vocabulary out of the way that each of the dots is called a vertex. Each of the lines is called an edge, and all together, when they are combined together to connected, they are called a graph. So this is a graph from now on your. Um, by the way, you don't need to write any of this stuff down because I'll be posting this later, so you guys can see it and follow along on your own time. So you don't need to take any notes unless you absolutely want to. Not the way that I've designed this. So we have a graph of vertices and edges. Vertex is singular, vertices is plural. Remember, make sure you remember that's an English term. So here's what I want to do. I'm going to show you one more vocabulary word, and this is your first question of the day that you'll need to answer. And look at the graph that I have right here. Not only did I draw a graph, but I put a number in each vertex, and what that number represents is called a degree. Not like a college degree. It's called a degree. Looking at the numbers and how there's a reason for each one of those numbers on there. I want you guys to look at the graph, see if you can tell and describe what a degree means. And you can actually do that on your phone or on your tab. Make sure you press the answer question and put in a response. You got about 60 seconds. See if you can come up with a response. Again, this is part of your participation grade for this assignment. So instead of assigning you guys homework, you're going to be graded on whether you participate in this or not. Don't worry about being right or wrong. We're not worried about that right now. At a certain point when we do quizzes later, yes, worry about being right or wrong. Right now, that does not matter. Put an answer in your responses. If you have not logged in yet, which I'm missing a few of you, here's the link again in the chat. Look in the chat, click the link. It'll take you straight to this presentation where we're at. Put what you think those numbers mean. A couple of correct answers already. I've got two screens up, so that's why I'm looking away. I'm looking at your answers on my other screen. It's just a lot easier. Good job. A lot of you are putting, a couple of you are putting in the angles. And good guess. We're not. This isn't geometry, so remember, get geometry out of your head. Get algebra out of your head for right now. Look at, see if you can see a pattern. Good. Some of you are getting this. Good. Uh, Five of you are not, or four of you are not logged in yet. Click the link in the chat to get logged in if you want to get credit for participation today. If you need help, send me a message or unmute yourself because you're not if you're not logged in. All right, let's see if this works. I've highlighted a couple of responses. Let's see if you see this on your screen. Check your screen out. How many edges are connected to a vertex? A degree is the amount of lines that connect to a point. The amount of lines that intersect at that point. Number of edges connected. All these, yeah. If you're lagging, guys, don't worry. It's not going to be kind of against you. Just make sure you're logged into it because it records who's logged into the presentation. I'll be able to tell. Yeah, guys, this is actually those four responses. There's a couple of you got it right too. I just didn't get a chance to star them. But that is correct. It's the number of edges that touch that particular vertex. Obviously, you can see the number 0 has no edges coming to it. This one on the top left only has one edge connecting to it. One I wanted to point out, look at the number 5. Look at the vertex with number 5. It has 1, 2, 3, and it has this curved edge which touches it twice, and that is a possibility too. So there's a degree of 5 there. So the degree comes into play into a lot of different things, and we'll revisit that later. That's just one of the first things I wanted to have you guys do. All right, moving on. So obviously, why does this matter? Well, over the course of the next 6 weeks, we're going to be doing this unit, and we're going to try to model a variety of different situations. Your Google Maps, your Google Navigation, your Waze app, your Uber app. Somebody brought this up, Uber last period. Whenever graph theory, these graphs can help represent maps so that they can figure out the best way between 2 points. And that's exactly what your navigation app does. You can model different types of networks like internet networks, friendship networks on Facebook or Twitter, UPS and FedEx shipping delivery routes. If you're a UPS delivery person, you leave the delivery office or the shipping center and you try to find the best route to drop off all of your packages and then get back on a timely manner. Obviously, UPS has this software built into the GPS that's finding those best routes for you. But that's the idea behind what graph theory does, using these dots and lines to try to find the best routes to that. So we'll, over the course of the next couple of weeks, we're going to see how that actually plays into that. So I like to start out the school year with this logic problem, and it's called the Seven Bridges of Königsberg. This city, Königsberg, was in Prussia, which is now Russia, and it had there's a big river that ran through the middle of the city, and there were 2 big islands in the middle of the city, and they were all connected by to the mainland with 7 different bridges total. This is a historically notable problem. It's a logic problem in math, and where you try to define a way to walk around the city, walk over the bridges exactly once, and ultimately visit all the different landmarks that there are in the city. And it's a big historical city. So that's what you guys are going to do. So your screen or your phone should let you, again, for those late people, there's the link again. The screen or your phone should let you draw on the screen. And here's what you're going to do. You're going to pretend that you're a resident. And here's a map below that I kind of simplified. You can start anywhere, and you're going to try to cross every bridge exactly one time. Okay, you can't go over a bridge more than once, and you can't swim across the river. You can only cross every bridge exactly once. So you can either draw with your cursor if you're doing it on a computer, or you can use your finger on it if you're doing it on your phone. It should let you draw on top of the screen. And I can see your answers as you guys are doing it. Hopefully this draw feature worked pretty well last period. I think it's pretty cool. So I'm going to give you guys about a couple minutes to see if you can find a solution to that. If you have any questions, unmute yourself or put it in the chat while we're waiting for people to submit their answers. It's funny seeing the answers pop up and then you, I guess, erase something or you delete it. When you clear it and start over, it just like goes away on my end. Here's one, although where I guess we start here. I guess somewhere up here by A, it looks like it went over the river. Close. Does anybody hate these types of logic problems? Like they get frustrated, Maddie? What's frustrating about them? I'm gonna give you about maybe 60 more seconds, and I'll show you what the correct answer is. Normally, if when we're in class and I do this, um, and normally when we're in class and I do this, we do it on the board, and I have people come up to the board. I put it on the white board on the overhead. Jaden, this is hard. What the heck? All right, you guys ready for the correct answer? You want me to show you how to do it? All right, I can't see everybody at once, so if you're not in your head, I might not see you. But I hate don't hate me after this, guys. But did anybody just think or know that it's not possible? Yeah, this particular problem is not possible. Now that doesn't. There's no solution to it. To what I asked you, Matt. Are you in the right spot? Matt, are you supposed to be in here? Okay, we come back later. Um, that's not. This is. I wasn't trying to trick you guys too much, other than the fact I want you guys to see that a lot of the problems that we do, or a lot of the things that we do in this class, and especially with in terms of this stuff, like it might not always have a solution, and not having a solution is okay. That's why I didn't do it. There was no way to get through all of it. Okay, not having a solution is okay. That doesn't mean that every time you can't figure something out, that means that there's no solution. That just might mean you might not figure it out. But I just want you to see that there is a possibility. Um, so basically, this guy back in the 1700s, his name was Leonard Euler. He saw this problem and he pointed out that it doesn't matter which way you choose to go. The only important feature of traveling through these bridges is what sequence that you traveled across. And so basically, what he did was he converted those bridges into a graph. And so those graphs that I showed you, this is one way you can use graph theory and it's to finding routes and whatnot. What I want you to do right now is in the chat, look at the graph, look at the map, which is the one on the left, and look at the graph, which is the one on the right. Obviously, there's four vertices, one for each landmass, A, B, C, and D. In the chat, put this, because I didn't ask this as a question. Which vertex, the top, bottom, left, or right on that graph, has to be island B? So which vertex, top, bottom, left, or right, does the B island have to be? Which one has to be B? Go ahead and put that in the chat. Let's see what people think. Taylor, can you unmute yourself and tell me why you think it's the left one? Are you typing it? Oh, it doesn't work. Okay. Let's. Oh, why don't you type your answer then? Why do you think it's the left one? Looks like everybody picked the left one. Why the right one? Bottom one? You like to be different, huh? Okay, so Taylor said it's the left one because that's how the islands are put. I'm not sure. Okay, let me call on somebody else. That Jeremiah, will you unmute yourself and tell me why you said left? So in particular, how many were there? And was there any other landmass that had five bridges connected to it? No. Yeah. I mean, it should. You guys saw it pretty easy. You may not have been able to describe it as easily, but you're right. You guys are right. You were able to visually see that B has five bridges connected to it, so the left vertex had five edges connected to it, and that was the only one that was like that. So it was pretty clear that that one had to be the one that was B. And so these are the cues that we're going to see as we start creating these graphs. Um, so, and I'll just skip that. So here's what I did. Here's a multiple choice question, and you don't have to put this one in the chat. Don't put this one in the chat. Put it on the screen. All of the graphs are different representations of those bridges except for one of them. Which one is the one that's not representative of those bridges and islands? 1, 2, 3, or 4. You can put the answer in the Pear Deck slides. Pick which one you think is the one that does not represent the bridges based on what we just talked about with that vertex B. Got 7 people answered so far. Crystal, don't put it on the screen. Everybody can see that. Don't put it in the chat. Put it on the Paradex slides. Angel, are you logged into the Paradex slides? Waiting on 6 more people to answer. Yeah, nobody's ever learned this, Angel. This is brand new this year. This is the first day you guys are seeing this, probably in your whole life. All right, one more person waiting on one more answer. All right, let's see. Let's see how we did here. Whoa, we're split between graph one and graph three. More people pick graph three by one person. So let's take a look at this. Does each of these graphs have a vertex that has a degree of 5? And graph one does. This one on the top right on graph one has 1, 2, 3, 4, 5 vertices touching it, which has to be that island B. But graph three does not have any vertex that has 5 vertices touching it. So graph three cannot possibly be a representation. So if you got graph three, bravo, good job. First time you've seen it, obviously, but don't worry. This is why we're starting this out like this. Um, so I want to show you guys how to draw a graph from something that being given to you. And I'm going to take an easy thing, pick a map, and we're going to turn it into a graph. And I'm going to do it for you guys first, and then I'm going to have you guys practice it right afterwards. Um, so basically, here's the south central states of the United States. Hopefully, you guys can name all 6 of those states. They're at least the ones that surround Texas here. And the first step in creating a graph from something like a map is to draw a vertex for each point of interest. In this case, they're the states. So I'm going to draw a vertex for each of the 6 states. There's 6 highlighted states there. And I'll just spread them out. It doesn't matter where you put them when you're drawing them. If we were in class, we would be doing this on paper. Obviously, this is a little different. And then I would label them. Next step would just be to label them. That way we can keep our affairs in order in terms of making sure that we connect the right places to the right vertex. So I labeled each state, each vertex with a state. And then the last thing really is to connect the states with an edge if they share a border. So I just go from left to right. I like starting the way I read. And so the first state that I see left to right is New Mexico. And New Mexico shares a border with both Texas and Oklahoma, even though the Oklahoma one is very small. So I'm going to draw an edge in between both Texas, or New Mexico and Oklahoma, and then New Mexico and Texas. And those are the only 2 states that New Mexico touches. So I'll just go to the next state. The next one, obviously, Texas. And Texas borders almost all of them. So I'm going to draw an edge between Texas and all the other states that it borders. It's already connected to New Mexico, but then I've got to add in Oklahoma, Arkansas, and Louisiana because it borders all of those states. Oklahoma also borders Arkansas, so I'm going to connect those 2. And then Arkansas borders both Louisiana and Mississippi, so I'm going to connect those 2. And then finally, Mississippi needs to be connected to Louisiana because they share a border as well. And now my graph is done. And if you look at that graph and we talked about, hey, these are states that share a border, well, we know that the 2 states that are connected, if they share a border. If they're not connected, that means they don't share a border. So this would be the simple way to draw a graph for a map, which we will be doing later on this unit, especially when we start to get into map coloring, which is a really cool concept. So I'm going to have you guys practice. Take about 5 minutes, and don't worry about being super nice and neat. I know some of you are just drawing with your finger or your cursor. You're going to draw a graph in this space below for the 7 countries of Central America. Don't do Mexico or Colombia. That's not Central America. So only the ones that are colored. Abbreviate. I picked this map because every country starts with a different letter, so you can just use the first letter of the country to abbreviate. Draw your 7 vertices. Spread them out as you start to draw these because you want to connect them with lines. And make sure that you're drawing it correctly. You only connect the vertex if it shares a border with another country. So draw a graph for Central America. There's only 7 countries there. You can just abbreviate Abbreviate if you need to. Make sure you label before you start connecting. Make sure to label before you start connecting so that you know what to connect. Just abbreviate with the first letter of each country because they all start with a different letter. And I'll be going through your responses here in real time. Zach, make sure you spread your vertices out. A couple of you too, Gracie, spread. It'd be a lot easier if you spread them out across the whole. Good job, Jeremiah. Spread them out. It'd be a lot easier to connect. Trey, you got to make sure you label. Guys, make sure to label the vertices before you start drawing the edges in there. If you're not sure, send me a private chat. Nice, Daniel. I like how you color coded it. That's another thing that we'll be doing. Gonzalo, the green one is Belize. Nice. Nice, Dominic. Some of you getting creative. Christian, Crystal N, are y'all there? You haven't started yours yet. I'm gonna pop up a few of the correct answers here in a second for you to. Don't worry about being wrong just yet, guys. Like I said, try, work on it. We'll have some more practice on this stuff. So I know it's all brand new. That looks good. It's cool. I'm gonna show some of the responses here. This one was just color coded with there. You know, if you can definitely go back to the map and see the color code there. Here's all the ones that are labeled, look something like that. These are all correct answers that look different. Obviously, I think they're mostly correct. They look a lot differently because these can actually be, they don't have to look the same. They don't have to look exactly the same. That's the beauty of graph theory. Um, Don't worry about your connection. We'll keep trying. Okay, so here's the next thing I want to do. Moving on with this and in practice. So um, here's a graph that I already created for you. Has anybody ever been to the Botanical Gardens in Austin, downtown off Barton Springs by the Zilker Park? Anybody ever been there? You walk around and I mean, they have a bunch of walkways and they have like flowers and sculptures and stuff like that, all the way throughout the walkways. So imagine that you're there and you're in this garden wildflower area, and the edges on this graph, so the lines on this graph are the walkways, and you want to see every display, but you don't want to backtrack. So backtracking means you can't go back down that same walkway. In this case, you can't go back down that edge. Each vertex represents an entry point, so you can enter or exit at any one of those vertices. I want you guys to trace a path where you would go through every edge or walkway exactly one time. Okay, it is possible this time. This one is possible, so I want to see if you guys can figure this one out, and then we'll go over the correct answer. So this is possible. Find a way to start at any one of those entry points, any vertex, trace a way to go through every edge exactly one time, and that's it, at one time. And then make sure you put in where you started and where you finished. Put a little star or put start and finish or S and F. It is possible. I'm not tricking you guys this time. This one is possible. Let's see if you guys can figure it out. Again, I wish we were in school. I'd normally have you guys working on something like this in a group. It's a lot harder now, but hopefully we'll get through this together. Make sure you go through every walkway, every walkway. So every edge, every line has to be going over exactly one time. It's possible. Savannah, that's not what I mean. Trace over the actual lines. I'll give you guys a hint. Start in the top left or bottom right. Start in the top left or bottom right. Good to know. Nice, Martin. Christian, good job. Brian, good job. Gracie, good job. Dominic, nice. It looks like most of you, everybody's submitted an answer so far, at least something, which is good. And a lot of you looks like you've gotten it. Awesome, awesome. So for those of you that didn't, I will run through this really quick. The solution that I came up with, this is not the only solution. There are several ways to do this. And so that's another thing about these things. Sometimes there's no solution. Sometimes there's multiple solutions. And so this is a good idea to go through. Here's where I started on the bottom right. Since a lot of you looks like you got this, I'm going to run through this pretty quickly. I went into this and I did this little triangle. Now notice how after these three walkways, I already ended back where I started, but that's okay. We still haven't gone over an edge more than one time. I then went left, completed that triangle. I went over and I finished that triangle, and then basically I ended at the top left part. You probably could have done the same thing by starting in the top left and ending in the bottom right. So multiple ways to do this particular problem. Um, so that guy Euler I was talking about, he's the one that really discovered graph theory, and so he figured this part out using that logic problem. He kind of figured this thing and he named it after himself. So a path, anytime that you go make a path through a graph that goes through every edge exactly once, so the no backtracking, that's called a Eulerian path. And so that's he named it after himself. Go over every edge exactly once. That's called a Eulerian path. So here's the last problem of the day. Here's the last thing I want you guys to do, and then we're done. Here's another graph. It's smaller this time, so it should be a little bit quicker. I want you guys to find a Eulerian path in this graph, but this time I want you to find a path that starts and ends at the same vertex. So start and end at the same spot. So find a Eulerian path where you use every edge one time, but start and end at the same vertex. And it is possible. It's definitely possible. Ooh, Maddie, that was quick. Good job. Kate, very fast. Good job. Ooh, Lino's already got it. Christian just got it. It's cool seeing this pop up on you. Marshall, nice job. Well, why'd you delete it? There you go. Jaden's got it. Brian's got it. See, the more we do this, Jeremiah, nice color usage there. It's a lot easier to see. Yep, good job, Taylor. I give about 30 more seconds for some of y'all to finish what you're drawing. All right. I mean, it looks like almost all of you got figured it out. There's multiple ways to do this. I think you can start on any one of these vertices and actually complete this. Here's where I started in the top right. I went all the way around the square. Then I came down the middle, and then it did a little loop-de-loop, and I was done. So this is a Eulerian path that's pretty unique. It uses every edge exactly one time, but it also starts and ends at the same vertex. So we have a new name for that. That Eulerian path now becomes a Eulerian circuit. So anytime that it starts and ends at the same vertex, it's a Eulerian circuit. I'm using every edge exactly one time. Boom. Okay, I'm going to stop right there because I want to get some feedback from